Ready-made maths YouTube mathematics training. Teacher and teaching assistant training. This week we're continuing our look at mental multiplication strategies. We're now up to day 5, factorizing. We've already looked at rounding and adjusting, at partitioning, and at reordering the calculation. And today it's quite specific. We're looking at how we can use factors to help us in our multiplication. In particular, how to help us making long multiplication considerably easier.
Hello and welcome to day 4 of the Ready-Made Maths YouTube training on mental multiplication. Hopefully, if you've been following the other videos, you'll remember that on day 1 we introduced all of the key strategies for mental multiplication and just briefly looked at each one individually. Since then, we've started with reordering and developed that strategy. We then moved on to the key default strategy of partitioning, and if you followed us yesterday, you'll have seen round and adjust. Today's quite a short video compared to some of the others, where we're going to be looking at the strategy of factorizing. Now, factorizing isn't normally a strategy you would associate with long multiplication. It's something that we just do. We find factors of numbers. But what we're going to do is take that idea of finding factors and this time use it as our starting point for multiplication of basically a 2-digit number by a single-digit number, or a 2-digit by a 2-digit number. Now, before we go into the visuals behind that, let's just start off just by looking. I've just randomly selected a load of sets of number cards. I'm just going to turn over a few of them and let's have a quick look at the factors of those numbers. So if I start off, what a great start, starting with the number 17. How many factors does the number 17 have? Hopefully you'll recognise as a prime number, it only has 2 factors, itself, 17, and 1. And you will notice on each of these cards that 2 of the factors are already there, but the others we'll have to work out ourselves. The next card, I'll use that one for later, is the number 42. Have a look at the number 42. How many factors does it have? What's the obvious factor that jumps out for any number? There's always one factor, a pair of factors that we should see straight away. Is there a times tables fact, a multiplication fact that we associate with 42? And can we derive any other facts from that? Just pause the video for a second. Let's have a quick look. Okay, let's look at the number 42. Well, what's the first pair of factors I'd be thinking of? I'd start off by thinking 1 and 42, or 42 and 1. Now, from that point, we can develop the doubling and halving idea. We're going to be looking at that later in the week as an actual strategy for multiplication, but it also works for finding factors. If 42 multiplied by 1 is one of the factors, if we have 42, we get 21, and we get 21 multiplied by 2. So that'll be a second pair of factors. Does 42 divide by 3? Well, actually, because the digits add up to a multiple of 3, 4 and 2 is 6. That's a general test for multiples of 3. So yes, 42 is also divisible by 3. It's 14 multiplied by 3. And last but not least, there should be a fact that jumps out straight away, which is 6 multiplied by 7. So 42 has got 8 factors: 1 and 42, 2 and 21, 3 and 14, and 6 and 7. So let's select a couple more numbers, we'll have a look at those, and I'm going to put some onto the board and we'll develop our understanding of factorising. 110 and 22. Now, what connects both of those? Is there a factor of those that jumps out straight away? And this is often a nice activity to do with children before we even move into multiplication strategies, just to discuss the idea of factorising. Can we see any factor that applies, a common factor of both numbers? Hopefully you'll see they're both multiples of 11. That's 11 times 10, as it says there, 10 multiplied by 11, and this one is 11 multiplied by 2. Now the number 22 only has one other pair of factors, 1 and 22. The number 110, however, has got, as well as 10 and 11, and as well as 1 and 110, does have other factors that we can derive from what we've already worked out. We know that it's 1 multiplied by 110, therefore, if we have it, we get 55, so 2 multiplied by 55 is another factor pair of 110. Is there any other that jumps out? Well, what about, we know it's a multiple of 10, it's also a multiple of 5. So, if it's 11 times 10, we double the 11, and we get 22. We have the 10, we get 5, so we also get 22. multiplied by 5. So doubling and halving is a brilliant way of finding factors of lots of different numbers. I'm going to come back to some more of those later on. What I want to do now is move over to the whiteboard. I'm going to put a range of numbers on there, and I'd just like to basically have a look at them and see how many factors you can find. And I'm going to basically set you a mega challenge for my favourite factorising number that I often use in class with children in upper key stage 2. And as you can see on the board, I've now put 12 different numbers that we're going to look at later on as part of the actual calculations. Before we move on to the calculations and the visual representations of factorising, I'd just like to get a few factors out into the open that we're going to be using later on. So I've chosen relatively straightforward numbers from all less than 100. What I'd like you to do is just have a look at those and just jot down as many factors as you can think of all those numbers from 14 to 75. And then we'll come back and have a look at the different answers. So let's have a quick look at that now. Let's take a look at the different factors of each of those numbers. Starting with 14, there's the very obvious 1 and 14, and then 2 multiplied by 7. Similarly with 16, the 1 and 16, double and halve give you 2 multiplied by 8. And 4, I haven't written 4 with the other 4 because obviously we're just looking at the factors, and 4 is the factor of 16, and 4 obviously goes with itself. 18, again you can see 1 with 18, 2 with 9, and 3 with 6. 22, just a double and half again, 1 times 22, 2 times 11. And I think the best example of doubling and halving you can see with the 20. 1 multiplied by 20, double the 1 you get 2, halve the 20 you get 10. So 2 times 10, and the same thing happens again to give you 4 times 5. 24 has got 8 factors, as you can see there. 25 has only got 3, 1, 25 and 5. 28 has got 6 factors. Again, doubling and halving works really well there. 1 and 28, 2 and 14, and 4 with 7. 32 has got 6 factors. 35 has just got the 4. And 75 has got 6 factors. 1 multiplied by 75, 3 multiplied by 25, and 5 multiplied by 15. The one that I've left is 72. Now 72 does have quite a lot of factors. Some are obvious because we associate them with multiplication tables, others less so. So what I'm going to do with number 72 is I'm going to just plot that one on a whiteboard and find out all the different factors of 72. And there we have the colour-coded factors of 72. What I've tried to do is just show that double and halving by using the 2 different colours. 1 multiplied by 72, 2 multiplied by 36, that moves us on to 4 multiplied by 18, and the one that we should know, 8 multiplied by 9. The other known fact is 6 times 12, and again if you halve the 6 and double the 12, that gives us 3 multiplied by 24. So 72 has got an awful lot of factors. And as we're going to see later, we can use any of those to help us with multiplication. Now, from the first time since we started the Ready Made Maths YouTube channel, I'm going to introduce you to my multiplication Abacus. I've usually been using the Slavonic Abacus for all of the other activities, but this is one that I've had kind of self-made really, and it created specifically so that it's got 12 multiplied by 12. So I can create all of the arrays for all the tables facts that children need to remember from 1 times 1 to 12 times 12. So rather than having the usual 10 going across, this actually does normally have 12 in each row. So what I've created now is a relatively straightforward multiplication calculation. I've created 10 multiplied by 6. And what I want to prove is how factorising works. Because if we start with the number 60, 10 times 6 is 60. We could just check it, 10, 20, 30, 40, 50, 60. I've got 10 this way and 6 this way. So 10 multiplied by 6 is 60. What about if I factorise those numbers? So what I've just done here is I've just factorised those numbers. I've factorised the 10 into 5 multiplied by 2, and I've factorised the 6 into 3 multiplied by 2, just so we can see the smaller factors of those numbers. So 10 times 6 becomes 5 times 2 times 3 times 6. Let's just prove that actually you will end up with the same answer. So what I'm going to do now at the bottom of the abacus is create 5 times 2. So I'm going to get 1, 2, 3, 4, 5. I'm going to multiply that by 2. That now gives me at the bottom of the abacus 5 multiplied by 2. What I want to do then is go to the next part, which is multiply that by 3. So 5 times 2 is 10. Let's multiply that by 3. That gives me 10 times 1, 10 times 2, and 10 times 3. What I'm finally going to do is get to the final factor, because if you remember, we started with 5 times 2 times 3 times 2. 5 times 2 is 10, 10 multiplied by 3 is 30, now I need to do 30 multiplied by 2. If I do 30 and get another 30, over here we can see a second set of 30, 30 multiplied by 2, as we can see, also gives me 60. So the first, obviously, that was what we started off with, which is 10 multiplied by 6. What we've now created is exactly the same array, but by building it up from the factors. So what we're proving is factors can be built up to make a much larger multiplication. What we're going to do now is look at the actual factorising strategy. Now I'm beginning by giving calculations that we could already do based on the previous training on the other days. 16 multiplied by 3 and 27 multiplied by 3. Now we already know we can use partitioning, 3 times 10, 3 times 6, 3 times 20, 3 times 7. But let's just look at how factorising could work, and would that make it even easier? Could we factorise 16? Well, what could we do? What do we know about 16? Well, we know that 16 is 8 multiplied by 2. So if I was to go 2 multiplied by 8 multiplied by 3 and write it that way, or another alternative is to write it as 4 multiplied by 4 multiplied by 3. So all we've actually done there is just factorised 16 and written it in 2 different ways. Suddenly, if we now use the reordering strategy that we've talked about before, we know that multiplication can be done in any order. Now let's start at this side. 3 times 8 is 24, doubled is 48. So the factorising just gives us another option. I actually think the next one's even better. 3 times 4 is 12, and 12 multiplied by 4 is 48. So again, for children that like to explore and really, try and see different ways to do a calculation, this is just a way of going to greater depth and finding an alternative approach for 16 multiplied by 3. Now, when it comes to 27 multiplied by 3, 27 actually only has 4 factors, 1 and 27, or 9 times 3. Let's just rewrite this one as 9 times 3 times 3. So our 27 has now been factorised into 9 times 3. Again, let's just read the calculation backwards. 3 times 3 is 9, and 9 times 9 is 81. We can double check it. 3 20s is 60, and 3 7s are 21. So it's a great strategy, and this is just a proof of how it can work with small numbers. We're going to develop it now with some other numbers to make it a little bit more complex.
So, as we've just seen in the ready-made mathematics classroom, factorising can even be used as a simple strategy for short multiplication. Now, as we looked at and as we mentioned in the classroom, we can use the partitioning strategy for either of these calculations. But it's quite nice to see, using the slides from the sense of number visual calculation policy, a very, very simple way you can jot it to show the children exactly what we're doing. This is the same calculations that we just did in the classroom. We can see the 16 has been factorised into 8 multiplied by 2. That then means, as we just saw, that we can do 3 times 2 first and then multiply that by the 8. Similarly, that's the same calculation we just saw with 27 multiplied by 3. As I've said many times before, the sense of number visual calculation policy allows you to print off each of these posters, use them up in the classroom on your working wall, and then use them as a kind of talking point for developing any other factorising strategies. So as I say, do take a look at senseofnumber.co.uk if you want to have a look at any examples of the visual calculation policy.
Okay, looking at the next one, we've now got 24 multiplied by 9. Well, we know we could factorise 9 into 3 times 3, but I don't think that's going to really help 24 times 3 times 3. So let's look, how could we factorise the 24? Then we'll look at 34 multiplied by 20. That's probably a more common one, and I think we actually use this factorising without even realising it's one of the standard strategies that we would always do. How would we do 34 times 20? Well, most people looking at that will go, well, I'll do 34 times 2 is 68, and then I multiply that by 10 to get me 680. What you've actually done in that strategy, as well as making it 10 times bigger, you've actually just used the factorising strategy. You've rewritten the calculation as 34 multiplied basically by 2 multiplied by 10. Or, some people do it the other way around, 34 multiplied by 10 multiplied by 2. But usually it's double 34 is 68, make it 10 times bigger, 680. Alternatively, the other way around, 34 times 10 is 340, doubled is 680. Let's go back to that first one now though. Let's pause the video. Which would be the better, or the best, sorry, which would be the best factors of 24 to use to make 24 multiplied by 9 a little bit easier? Have a little look and write down what you think. Now, what I've written down on the board are the 3 possible options that you could use for factorising 24. Which of those would make that calculation easier to do? Again, if we start reading it backwards, there's 3 times 8, or 8 times 3, 4 times 6, or 6 times 4, and 2 times 12, or 12 times 2. Again, because we can rearrange them as we looked at on the second day, we know we can multiply those in any order. Let's have a quick look. Well, with this one, we can do 9 times 8 is 72, and multiply that by 3, but that's not much different to what we started with, really, in levels of complexity. We could do 9 times 6 is 54, and then times that by 4. I like that one, because we can double and double for that. So 9 times 6 is 54, doubled is 108, and doubled is 216. I quite like that as an option, but I think the best option is definitely this one. It's a known fact. 9 times 12 is 108, and double it to make 216. So I think what you can see from that is actually we can do a partition, 9 20s and 9 4s, but there are other alternatives that will make the calculation easier if we just use a factorise. Let's take this activity now a stage further. I'm going to give you now 4 different calculations to look at using some of these numbers from over here. So let's have a look. I've taken 4 of the smaller numbers, 12, 14, 18 and 22, and I've chosen another number to multiply them by. What we're going to do now is look at each of those 4 calculations and decide which number am I going to factorise out of the 2, because I could factorise 35 or 12, 45 or 14, 35 or 22, etc. And is there a way by factorising it I can make the calculation easier to do? There's probably several examples for each one. There's not going to be one right way of doing it, but it's really good at getting that depth of thinking going and allowing children to really see links between multiplication. It's probably, strategies we've never used before, and these 2 in particular can be factorised and made far, far easier, so they can be solved really, really quickly. So I'm going to give you, obviously a couple of minutes, pause the video, have a look at all 4, jot down some factorises, jot down some different factors of the numbers, and try and find an easier way to solve each of those calculations. Now the first calculation and the second one actually lead to 2 of my favourite strategies. 35 multiplied by 12, well, I could factorise the 35 actually into, I could write it as 7 times 5 times 12. And interestingly, reading that one backwards, 12 times 5 is 60, and 60 times 7, using 6 times 7, would give me 420. So that's one way I could do it. That's an interesting one. But I think there's an even better one. Let's factorise the 12. Let's factorise the 12, and we're going to read this one in the correct way. 35, and we're going to make that 12, 2 times 6. Suddenly, we've got a very, very easy calculation. 35 doubled is 70, and then we end up again with 70 times 6 is 420. So that gave us 60 times 7, that gives us 70 times 6. Now, as I mentioned right at video 1, we've got to first of all have covered the idea with the children that if I know 6 times 7 equals 42, then 60 times 7 equals 420. That needs to have been covered first of all, and that's part of the year 4 curriculum with smaller numbers to look at multiplying by a multiple of 10. That obviously needs to have been covered first, but then how easy are those calculations using that strategy? Let's now have a look at 45 multiplied by 14. Again, if I set the same idea, I could factorise the 45 similarly into 9 and 5, but I think it's much, much easier just to factorise the 14. 14 factorises into 2 times 7. Straight away, 45 times 2 is 90, and 90 times 7 is 630, because 9 times 7 is 63. 63 tens, 630. What other strategy would you have used? You might have done 45 times 10 and 45 times 4. you might have used a column method or a standard method, but now we'll look at it and go, wow, how easy is that? 45 times 2 is 90, 90 times 7, that is 630. Let's take time now and look at, can the same thing be applied to 350 multiplied by 18? I'm going to rub that clear now. Now 350, we've got 35 up there, it's the same principle, isn't it? 35, if I look at 18, I'm going to factorise it. I could factorise it into 6 times 3, or I could factorise it into 9 times 2. I think using that similar doubling principle, I'm just going to write that as 350. I'm going to factorise my 18 into 2 and 9. Again, we've actually got a very similar calculation to what we've got up here. 350 times 2 is 700, and 700 times 9 equals 6,300. Again, really easy. We've made something that looks really complex, and we've done it in a couple of seconds just by using that idea of factorising. So with the smaller numbers that we looked at earlier, probably the partitioning strategy was just as good, if not better. But as the numbers get bigger, you can see how this strategy can really help. Let's look at the final one, 35 multiplied by 22. Now I could try this either way around. I could do 35 times 11 times 2, or I could factorise the 35 into, for example, 7 times 5 times 22. Again, let's just pause the video and look at both of those. I'm going to clear the board, so we've just got that calculation on. Have a quick look at that calculation and see how would you do that and how would you do that.
And as you can see, the sense of number visual calculation policy also includes examples of long multiplication. I won't go through the answers or the strategies as we've just done them in the classroom, but I just wanted to show you that these particular examples are part of the particular policy. In the classroom, we've done a lot more, but there's these ones that you can fall back on, print out, and use as part of your working walls.
Okay, I've just written both those calculations there to have a quick look at how would I do either of those. Well, if I was doing 35 times 11, I do have a little trick that helps to do 35 times 11. There is an explanation behind the trick. Just for the time being, I'll just show you the trick and then we'll have a quick look at the explanation. The little trick is if you're multiplying a 2-digit number by 11, the number is 35, so I write down the 3, I write down the 5, I add the 2 digits together, which gives me an 8, and I put that in the middle. The reason that actually works, a brilliant little trick, the answer is 385. The reason it works is because 35 times 10 is 350, and 35 times 1 is 35. So what you actually see is because the 35 has got 10 times bigger, you see the 3 ends up in the hundreds, the 5 ends up in the ones, and you end up with both the digits in the tens. But it's much easier just to say, well, 3 and 5 is 8, and put that in the middle, because that's what you would end up with by doing it that way. So it's just a nice little trick that I use an awful lot. Children in years 4, 5 and 6 love that little times 11 trick. 35 times 11, 385, and I'm just going to double it. Now it's not an easy calculation, but we can double 300 to get 600, double 80, 160, that's 760, and 10 is 770. That's one way to do it. The other alternative with factorising is, I think this is slightly easier. 5 times 22, well 5 20s are 100, 5 2s are 10, so we end up with 7 times 110. I think that one's easier. Again, 11 times 7 is 77, so 110 times 7 is 770. When you're looking and thinking, wow, that's quite complicated, look at what we started off with. 35 times 22, we've just factorised it really quickly, we've done a little bit of mental maths, we've saved myself a lot of long multiplication work. So I think it's a really, really nice strategy. I'm just going to write a couple more up and then we'll just develop it into higher level numbers and then we'll conclude for the day. So we really are moving into a year 6 plus now. Looking at these, again, these can be done with long multiplication. You know, children need to know how to do that as well. But these two calculations can be made far simpler using the factorising strategy. I have chosen the numbers 25 and 75 because there's something very special about those numbers. Let's have a look. Again, there's far more than one way of doing this. Can we factorise the 25 and make that work, or can we factorise the 36 and make it work? Can we create much easier calculations than a long multiplication? Again, as we move to 75 multiplied by 28, do we need to factorise the 75? Do we need to factorise the 28? Or do we need to factorise both? have a look, just have a little play. As I said, there's many different ways to do these. You'll see other ones that I won't show you that will also work equally as well. But it's just playing with numbers and developing an alternative strategy. So let's have a quick look. I absolutely love this first calculation, 25 multiplied by 36. I've started with probably the easiest way to do it, which is just to keep the 25 on its own and to factorise the 36 into 4 times 9. I can then straight away go 25 times 4, 4 25s are 100, multiplied by 9 gives me a product of 900. That's a really simple way of doing it, and I could have done something similar with using 6 times 6, but that was definitely the easiest one of the three. Alternatively though, I could actually factorise both numbers. So if I factorise 25 into 5 times 5 and factorise 36 into 4 times 9, then I need to decide what order to multiply them. So I'm going to start with the 4 times 5. So 4 times 5 is 20, times 5 is 100, and we're back to 900 again. Similar, just done a slightly different way. What if I'd chosen to make my 36 6 times 6? Again, if I start from here, 6 times 5 is 30. 30 times 5 is 150, and then it's a little bit harder, 150 multiplied by 6. I probably wouldn't choose that one, but it does get the same answer in a different way. But what I do really like is the one at the bottom here. 25 is 5 times 5, 36 is 12 times 3. What I'm going to do now, again, I'm going to start here. 12 times 5 is 60, 60 times 5 is 300, because 6 times 5 is 30, and 300 times 3 is 900, so I think that one's almost as quick as the first one. It's just really nice to open up our mental fluency. Let's now look at 75 multiplied by 28. Again, a range of different ways. We could do 75 times 28. We could start off by making 25 multiplied by 3. And in fact, I'm going to rewrite that slightly differently. Just let me change that one. I'm going to make it 3 multiplied by 25. And I'm going to make my 28 4 multiplied by 7. At that point, you can see what I've got again in the middle. 25 times 4 is 100, 100 times 7 is 700, and 700 times 3 is 2,100. I could have just left my 75 as it was, and just done 75 times 4 times 7. Again, I'd need to know how to double and double again, but 75 doubled is 150, doubled is 300, times 7 is 2,100. Now, whichever way you choose to do it, and again, there are many others, that is so much easier than trying to do a long multiplication with 75 times 28. In particular, this one here. It just makes the calculation so much easier. So I've just got 2 more for you to look at, which are a bit more complicated, but I just want you to think about this from obviously a high-level upper key stage 2 child, and how we could ask them now at real greater depth, simplify the next calculation. And here are our final 3 calculations to have a quick look at. 54 multiplied by 16, 26 multiplied by 32, and 72 multiplied by 24, and a much more complex one. We'll take the first one, 54 multiplied by 16, hopefully using the idea of the doubling one. So 54, oops, let's get a pen that works, will be useful. 54 multiplied by 2 times 8. Straight away, 54 times 2 is 108, and that one we can do straight away. Just look at the difference between those 2 calculations. 8 times 108, 864. So I think that one was quite an easy one to do. The other 2, again, I'd like you to have a quick look at. There's going to be quite a few ways to do it, but can we find the easiest one? 26 multiplied by 32 has got less options. 72 multiplied by 24 has probably got about 100 different options, but let's see if we can find one that makes it simple. I'll just show you, 1 or 2 examples and just let you see if you agree. So have a quick look at those, and then we'll just pause the video now. So let's look at these final 2 examples on the board. I think 26 times 32, I could factorise the 26 into 13 times 2, but multiply by 13 isn't particularly easy, so I think it's much easier to factorise the 32. Again, I could go into 2 times 16, but I think it's easier to go into 4 times 8. From that point, we can just do it in order. We can do 26 multiplied by 4. So we double and double again. 52, 104, and we end up with 104 multiplied by 8, which is 804. and 32. Again, there are probably many other ways to do it, but I think that one's probably the easiest. Looking at this example, 72 multiplied by 24, there's so many ways to do it. There's so many factors of 24 that we could use. I've chosen to use the 12 and the 2, again, because I've got this little fact in the middle. I've factorised my 72 into 8 times 9. I've factorised my 24 into 12 times 2, and I can take those two numbers in the middle. 12 times 9 is 108. 108 multiplied by 8, which is the calculation we had over here, equals 864. And to finish off with, we have 864 doubled. So 800 doubled, 1,600. 60 doubled, 120. And 4 doubled is 8. So 1,728. You may well argue that that one could be done just as quickly with a long multiplication, but this is more of a greater depth activity just to explore different answers. I still think that's quite a nice way, and it just opens up multiplication. So I hope you found those, they did get more challenging as we moved on, but the idea of this particular activity is not just to develop mental strategies, but to go to some greater depth as well.
So again, we can see from the visual calculation policy examples of factorising at greater depth. These are similar to the ones we've just been looking at, 26 multiplied by 32 and how that can be simplified, and even an answer that goes over 1,000, 52 multiplied by 24. How's that one been factorised? Well, we didn't factorise the 52, we factorised the 24 into 4 multiplied by 6. That meant we could very quickly double up twice to get 208 and multiply those two separate parts by 6. 6 times 200 is 1,200 and 6 times 8 is 48. Again, we could have factorised the 24 into 8 times 3 or into 12 times 2. I think in this instance that's probably the easiest one that we could have chosen.
Thank you so much for joining me for the 4th day of the mental multiplication strategies. What we're going to be doing tomorrow is we're going to be moving into some doubling strategies. We've already been using them a little bit in some of the other videos, so tomorrow we're going to look at a range of different strategies involving doubles. Thank you so much for joining me, and I'll look forward to seeing you tomorrow.
Let's have a quick brief look at the strategies we've seen so far. Well, we started day 1 with a look at all of the strategies. Day 2, we looked at reordering. Day 3, we looked at partitioning. Day 4, we looked at round and adjust. And then today, we've looked at factorising. Tomorrow, we're going to look at a range of different strategies that are all connected with doubling. So, I hope you've enjoyed today. Tomorrow is doubling strategies. I hope you'll join me as we're going to take a very brief look at a few different ways to use doubles to help us with our long multiplication. Thanks for watching, and I'll see you tomorrow.